Hi guys, this is Neurizon Progressive Jackpot LED Display Hacking Part 3. This is the conclusion of a real-time set of 4 videos concerning hardware. In the last video we left off cycling through the 8 lines of each module using a decade counter and the onboard totem transistor drivers. The result was the ability to be able to set arbitrary pixels in one row of LED controllers that I can communicate with serially. I temporarily used a fairly bodgy set of connections to one row of cascaded serial shift registers that control a row of 10 8x8 modules for testing. There's another 5 rows of 10 controllers each that all need their latch and clock pins buffered and all need individual serial input connections. So there's a lot more connections to make to this footprint to control the entire display. A whole bunch of latch and clock connections as well as serial data connections. The serial clock and latch pins will all be delivered synchronously, so they'll all be buffered with the chip that I soldered onto the circuit board in the last video, but in this one it'll actually be employed, the quad half H bridge driver from Texas Instruments. Any connection made between the PGA footprint and PGA Simulator 2000 will be made through a little PCB tag strip. It'll probably become obvious why I'm doing that later on. This is in fact all of the connections that cover the serial clock and latch lines from the 50-way IDC connector through the PCB footprints or vias, through PGA Simulator 2000 and back to onboard footprints to reach the LED display drivers. You can see on the left hand side of PGA Simulator 2000 the green and yellow wires coming in and out are just inputs and outputs for the serial latch and clock lines that just have heavier transistors that are able to switch high current to fan out to 60 ICs. There's another small breakout board beside the display to make connections between the 50-way IDC connector and the IC footprints for serial data lines. This was to save soldering a few more eyelets and pads that lead to the 50-way IDC connector, so there'd be less crowding in the IC footprint. A few of the IC footprint pads that I had to make connections to were next to each other in a way that I could bridge them, so that was handy, such as when a latch output from PGA Simulator 2000 has to connect to 2 rows and the pins for the 2 rows are beside each other. The very last connection I had to make was right above this black one in the middle, so I had to use an eyelet for that. It's hard to get this shot lit properly, but I'm trying to show that there's a breakout board either side of the IC footprint, so one between the 50-way IDC connector and the footprint, and another between the footprint and PGA Simulator 2000. You might have noticed I didn't make any connections to the smaller IC footprint close to the IDC connector. All of the serial data communications are made through this chip, so who knows, maybe it was there to prevent it receiving instructions from strangers. This is the first test, so experience it with me. I haven't done anything much to the software other than write the same gibberish as before. The decade counter's doing its job cycling lines, but the latch or clock isn't. It seems the extra buffering on PGA Simulator 2000 has added enough propagation delay, or the sum of propagation delay and transistor switching time, to require a small delay between the latch pin toggle. And with just that small change to software, everything appears to be working. So the clock and latch pins have to be buffered to every chip. The cascaded rows of serial shift registers all have to be receiving data, and we can cycle lines, so we have what could conceivably be an off-the-shelf product as an LED display, on paper at least, maybe not with this kind of workmanship. This is the final version of PGA Simulator 2000. I don't know if there's any change from the photo before, but one change through this process was tying down the unused inputs. The chips are upside down in this photo, but I've decided as a module this is the right way up because that's the way that I had to deal with it most of the time. I'm feeling exhausted as usual, but also kind of calm and happy and not tense like I have been for the past few days because I've got a result and achieved a certain stage. I don't really have any coherent frame buffer or software interface for this yet, but I like the idea that I'll be working with my own stuff from now on. To finish up this hardware set of videos, there's one more thing, potting, or encapsulation you might call it. Potting compound, potting mix. This one comes in a bag with a divider between the two parts, and when you separate it and then knead it out, you can start pouring it out of the bag. I've made a little bit of a well here out of coax goo with a deliberate place to overflow there because some of the pads where the connections are made are very close to the edge of the board. So I've got a piece of paper to catch any stalactites that'll come off, and they will. The breakout boards on either side of the IC footprint could still be worked on, but I'm interested in protecting the really fine work on the footprint, which I'd eventually break while programming for the thing or making changes to my own hardware, and I wouldn't want to invest a whole heap of time into it only to have it break. 24 hours from now I can fold those wires away neatly, tuck them away somewhere, but for now I'm just letting them hang naturally where they were. For now it does look like this is going to set in position where it is. It's tricky sometimes. You can heat it up to cure it sooner, but that will make it more runny. So I just tend to leave it in room temperature for 24 hours. So that's it from now. I can't do any programming, not immediately anyway. Bye for now.